Welcome back. In this video, we're going to pick up on our metapopulation model, and we're going to make some slight adjustments to it so that you can model metapopulation dynamics with either internal colonization or the rescue effect, which controls extinction. Jed just talked about these in his lecture, and so our goal here is to think about how we would make these modifications to reflect these two different kinds of metapopulation models. Let me just review where we've been so far. We set up a landscape that has 4x4 rows and columns, and we also established a probability of local extinction. That's given in cell B9, and a probability of local colonization that's given in cell B12. Given how many patches are in the system, we then simulated the occupancy and vacancy of patches through time. Here we're looking at the time step t, and in the next grid below it, we're looking at the dynamics in year t plus 1. And what you can see is that given these parameters that are inputs, we see that some patches that were empty in time step t can become colonized in year t plus 1, and some patches that were occupied in time step t become vacant or locally extinct in time step t plus 1. And some patches, of course, remain constant in whatever their status was. Now, the equation that we used is in cell P16, and we copied that equation through the whole grid. And this, in fact, is the island-mainland model. That is, it's the equations that generate your patch occupancy pattern in the next time step. And it has assumptions. So let's review this model, and then we'll be able to make some adjustments to it. This model is basically doing this following thing. It's asking, is the cell occupied or not in the previous time step? If it's not, then we're going to colonize it if a random number is less than cell B12, the probability of local colonization. If the random number is less than that, we're going to flip the 0 to a 1 and now let that patch be occupied. Otherwise, we'll keep it 0 and it remains unoccupied. If the patch itself is not 0, we're going to conduct this portion of the equation. It means the patch is occupied, and now we're going to consider whether or not it goes extinct. If a random number is less than the probability of extinction, then we'll say that the patch went extinct, and we'll flip the 0 to the 1 to a 0. Otherwise, we'll keep it 1, meaning that the patch remained occupied. So this is our mainland island model. And let's copy that and then paste that formula down someplace in our cell. So first I'm going to add a few headings here. Mainland island model. And I'll press the space bar and just paste my generating equation here. That's so that we can recycle this equation if we ever want to return to the island-mainland model. Now, Jed talked about another model, which is the internal colonization model. So this model focuses on colonization, and instead of colonization being fixed, this reference to cell B12, the probability of local colonization, we let it vary with each and every time step, and we're going to let colonization be dependent on the fraction of patches that are occupied in the previous time step. So colonization depends on F in the previous time step, and we're going to multiply it by this factor called I, which is a tempering factor. It's basically scaling how strong this effect actually is. So as a simple example, If the fraction of patches that are occupied is 1, then colonization might be 1. If the fraction of patches that are occupied in the previous time step is 0.5, then the colonization rate might be 0.5. We're going to multiply it by this factor, so if the factor I is equal to 1, then in fact the colonization rate is the fraction of patches. But if it's less than 1, we can temper that effect, and we'll see how that works in just a second. So I is the scaling factor for colonization, and you'll see that I added this in here already. And for now, let's just go ahead and keep it at 1, and that means that colonization is in fact F, the fraction of patches. So there's no other way that this system can be colonized. Instead, all of the colonization comes from within these 16 patches that we have set up here. Now, how will we take our equation in cell P16 and modify it so that it reflects this internal colonization? Put your video on pause and see if you can change this portion of the generating equation so that it now does not reflect to local colonization, but instead reflects the fraction of patches in the previous time step. I'll see you back here in just a minute. Well, the easiest thing you can do is just to replace the reference to cell B12 and replace it with the fraction of patches in cell Z14. So let's do that. So now I'm going to take this and I'll move it over to my fraction of patches. And now we're asking if a random number is less than or equal to the fraction of patches, then we'll let the patch become colonized. And of course we wanted to multiply that by I, and that's stored in cell B16. So we'll anchor that. And now this is our generating equation. And this, in fact, now is the internal colonization equation. Let's copy that. And press the space bar and paste it in. And now you see two different models for metapopulation dynamics. So here we say if the patch is vacant, which in my case it is, we're now going to draw a random number, and if that random number is less than the fraction of patches that are occupied multiplied by this scaling factor, then we're going to say that this site becomes colonized, otherwise we'll leave it empty. What happens when we change I? If we drop I down to some number, and I can range between 0 and 1, now when we draw our random number, we're going to take the fraction of patches and multiply it by I. And so we're really now shrinking the probability that we'll become colonized, because 0.375 times a half is a smaller number, and so we're decreasing our chances of being colonized. So if you make I large, then colonization is strictly a function of the fraction of patches, and if you make I smaller, then you're going to be decreasing that probability by some amount. Now, Jed also mentioned one more kind of model, and that's called the rescue effect model. In the rescue effect model, we're concerned about the probability of local extinction, and we're going to let that also be driven only internally, that is, dependent on how many fractions are occupied. So the idea there is, if there are a lot of patches that are occupied, then even though you may go extinct, you're going to be quickly recolonized in the same time step, and so therefore that extinction would not become apparent. Now, in the rescue effect model, then, I'm going to just move some of these up, we're going to say that extinction depends on F, and it actually depends on 1 minus F. And we also will multiply that by some factor, and that factor we're going to call E. So we'll add a new thing here, E, which is the scaling factor for extinction, and we'll let that be an input as well. I'll enter it as 1 for now. So this should make some sense. If all of your patches are occupied, then your extinction rate depends on F. So if 90% of the patches are occupied, then 1 minus F, which is 10%, would become your extinction factor. Now the E factor lets us temper how strong this fraction of patches mediates extinction. So let's click on cell P16, and now we're going to replace our original equation for those extinction that governs extinction, and we're going to replace this fixed reference to cell B9 with the fraction of patches. Why don't you go ahead and do that now, and I'll see you back here in a couple of minutes. Just like we did in the last exercise, we're going to now, instead of referencing cell B9, we're going to reference cell Z14, that's our fraction of patches, and we're going to add 1 minus the fraction of patches and then multiply it by E and anchor that reference to E. And now we've added a rescue effect into our extinction term. So this model actually includes both an internal colonization as well as a rescue effect on extinction. So I'm going to revise this to say rescue effect on extinction and internal colonization, and our equation now can be copied and stored here. So there you have 3 different versions. Of course, you can just do rescue effect and the mainland island model for colonization and mix and match these different clauses. I hope this gives you enough of an idea, though, of how you would change your generating equations, your main model equations, to reflect different assumptions about how colonization occurs and how local extinction occurs. And as Jed has said many times, you'd want to think hard about the species you're studying and try to choose a model that best reflects the system that you're interested in.
Great. Thank you, Terry. I hope that spreadsheet exercise was helpful to you in understanding the internal colonization and the rescue effect model. We've covered a lot of material in this module, and my hope is that you do have a better understanding now of metapopulations and metapopulation dynamics. So to wrap up, a few key points of the things we've covered. For one, a metapopulation is a population of populations. So it's a population of lots of what we might call subpopulations, sites, or patches. The metapopulation framework allows us to understand how some species live across a landscape. And we can describe a metapopulation based on the basic metapopulation model. And that basic model has a few key components. One of those components is F, the fraction of occupied sites, and we also have the components, both the probability of extinction and probability of colonization, that come into play. So that basic model allows us to describe a metapopulation, and if we can describe it mathematically with those components, then we can chart how a metapopulation may change over time. We can chart its dynamics, we can estimate equilibrium. We can estimate what it takes for that metapopulation to be stable from one year to the next. We ran through the basic metapopulation model. This model is sometimes called the mainland island model or the propagule rain model. And its underlying assumption is that the probability of colonizations and the probability of extinctions remain constant. So that's a good starting point for describing a metapopulation, but we see that there might be some more realistic perturbations on that model, some changes to that model that may be more appropriate for certain species and certain circumstances. So we covered two of those models. The first is the internal colonization model. That one assumes that the probability of colonization comes from within. Colonization is a function of F, or the fraction of occupied sites. The rescue effect model assumes that extinction now is a function of F. So it's not constant like the mainland model. It assumes that it's a function of how many sites are actually occupied. So with that, again, I hope you have a good solid understanding now of what a metapopulation is, how to play around with its dynamics, how to model a metapopulation, and how it's relevant to species management and conservation.